efficiency of harvesters with special respect to traceability. This will just be a general overview. The details will be given in the afternoon workshops today. So what is energy harvesting? Energy harvesting is usually understood to mean that you take free energy that is available in your instrumentation and otherwise would be wasted. And you can use it, for instance, in a car from the exhaust pipes, the thermoelectric harvesting as it is done by some companies already, or you can use some movement energy for light switches that remotely turn on lights. Or in a small scale, you can use the vibration power for monitoring vibrating industrial machinery, as Roy has pointed out in his slides. Energy harvesting is not large-scale generation from solar or renewable energies, but sometimes it is useful to have it as some sort of backup in small scale, some solar energy harvesters as well, to combine it to the so-called harvesting landscapes. And why should we all use energy harvesting? Roy has shown some good ideas. Otherwise, this energy would not be used. It's just waste energy, and we can use it to power small things and replace batteries. It allows to have wireless sensor networks, as pointed out, and you don't have to rewire that. You can get maintenance-free systems. You can have autonomous electronics, no need to change batteries, no cables. It's environmentally friendly because you don't use batteries and you don't have to take care to dispose them. And particularly, it may reduce the need for human intervention in remote locations. For instance, you can think about ocean buoys, which are used for some tsunami warning systems. Due to the movement of the buoys, you can generate energy to power up the sensors. So although the energy harvested is rather small, you can keep in mind that a small 100 microwatt energy harvester in its 20 years lifetimes can assemble 63 kilojoule, and so it will be able to replace over 50 button cells of the type CR2032. So this is one of the important points to reduce the use of these batteries, because they are everything else but not environmentally friendly. They have to be disposed separately. And here's an example how it is done in practice in cars. For instance, there's one car manufacturer that uses some thermoelectric device in the exhaust pipe system. And so this removes the need for the rotating generator in the motor and saves fuel and reduces the CO2 emission of a car significantly. So in our project, we dealt with two types of energy harvesting technologies. One is the mechanic energy harvesting. Mechanically, you can use electrodynamic harvesters. You can use piezoelectric harvesters, electrostatic harvesters, or magnetoelastic harvesters. And I've highlighted the piezoelectric and the magnetoelastic because these were the ones that we dealt with in the project. The second big technology is the thermal energy harvesting, where you can use thermoelectrics or pyroelectrics. And again, I've highlighted the thermoelectrics because this was one of the topic of the project. Now, the big point for energy harvesters is their efficiency. And so to characterize the efficiency or the effectivity, this is something that we have a lot of discussed during the course of the project. How do we define the efficiency of a harvester? And one of the important points is that you try to accurately measure the output power under defined operating conditions, so that you have some repeatable method to characterize the harvesters to define what you can get from them. And to do this, as a metrologist, to each measurement, you also have to do some uncertainty analysis to see what are the parameters that influence my measurement and how accurate do I know them. And for this case, you have to do something that sounds complicated. You have to develop a mathematical model to describe the measurement. But in most cases, it's just the equation how you calculate your output power. And with that mathematical model, you can identify the quantities that are to be measured. And if you have identified the quantities, then you can put in all the knowledge that you have about these quantities, including their uncertainty. For instance, from calibration certificates of the measurement instruments or manufacturer's specifications, and you can derive an uncertainty budget to estimate the measurement uncertainty. So for the efficiency, this is essential to obtain reliable and comparable results. As Jürgen has pointed out, we also did some round robins, and to compare results obtained at different places for the same quantity, to compare them, you need the respective uncertainties to see whether these values fit together. And having this, then you can compare the results, and this is really underpins the significance of your statement, how efficient is my harvester? So to calculate the efficiency of harvesters, you can consider the microgenerator as a black box and just define the efficiency. What power do I get out of my harvester compared to the power that goes into the harvester? And this is one of the challenges that we had in the project. Output power is mainly electrical, and this is something that is our common job. And electrical measurements are quite easy, but how to deal with the input power? It's either mechanical or it's thermal, and this was really challenging because most of us had no real idea how to measure it accurate, but we found ways together with other colleagues here at the different national institutes to get an idea how to exactly measure mechanical and thermal power. So for instance, for a thermoelectric harvester, here is some rough block structure of some kind of Peltier structure. You have your thermoelectric material here in the center, and it's between two copper blocks. One is the so-called hot side, the other one is the cold side, and you have a heat flow from, a heat flow from the hot side to the cold side through this thermoelectric, and this will give a temperature gradient across the thermoelectric, and according to this temperature difference, you get some electrical voltage at the output, and if you then have a load resistance, you can measure the energy that is drawn from that harvester. And so there's a simple equation to describe this efficiency. It's just the electrical power. Here it's the current drawn from the harvester times the load resistance in relation to the heat flow through the thermoelectric. But you see, here are some of the things that you really don't know. It's the heat that is dissipated, that's not going from the hot side to the cold side, but also dissipated to the environment, because you never have a good thermal isolation for these things. So this was that we concluded the determination of the flow of heat is difficult, and for thermoelectric materials, it would be a good choice to take the so-called figure of merit, Z times T, as a good choice to characterize thermoelectric harvesters, since the efficiency of a harvester is proportional to that figure of merit. And this figure of merit consists of three material parameters: the Seebeck coefficient, the electrical conductivity, and the heat conductivity. And these are the key quantities to be measured for thermoelectric materials. And how this is done, you will learn in the afternoon in the thermoelectric workshop. For vibrating harvesters, you have a similar situation. You have here, for instance, a piezo bender that is moved by a shaker and set into vibration. And if you change the frequency, then you see there is typically one point where this harvester is at its resonance frequency. And this is mainly the point where you get the optimum power from that harvester. But you can, again, quite easily measure the electrical power that's coming out of it. But what is the mechanical power really converted in that harvester? And you can have two approaches to that. One is that you just take simple mechanics and you have a moving mass and you know the acceleration and you know the displacement of the tip of this piezo bender. And from these things, you can calculate the mechanical energy. Or the other thing is that you integrate about the force. You do a force measurement and measure the velocity of the tip and calculate the mechanical power in that way. So for these types of measurements that you can do, you have seen you can have some mathematical equations that describe your measurement process. And so you are able to set up an uncertainty budget and putting in all the knowledge that you know, or all you know about the measurement setup and its properties. You have ideas of possible losses. These are the things that are incomplete sometimes, but you can give some estimates what's going on. And you need a calibrated instrumentation traceable to national standards and though traceable to the SI. And this traceability is only given if this service is offered by an accredited calibration laboratory or a national institute, a metrological institute that has for this special calibration a measurement capability and an entry in the so-called measurement calibration and measurement capability database at the BIPM, which are the ones that maintain the units for the world. Okay, for a simple piezo shaker, you can derive such a simple mathematical model. Again, here you have the electrical energy measured as the voltage that you can, derive from the harvester divided by the load resistance in relation to the mechanical quantities like mass, acceleration, the vibrating frequency, and the displacement of the tip. And then you can vary, for instance, the acceleration and measure the output power, which is this solid curve, compared to the input power, which is the parabola on the lower side. And if you divide them, then you get this graph for the efficiency. And you see that here at a certain acceleration, you have the optimum efficiency. But what you also can see at the point of optimum efficiency, you don't have the maximum of the power output. So this is something that we have to deal with in describing such a harvester, which is the optimum operating point for such type of harvesters. So when you have the mathematical model, you can also easily derive an uncertainty budget where you put in the quantities, the value that you know, I should not click, the values that you know either from a calibration certificate or as some sort of measurement results. Sum it all up and find that you can measure the input power to a certain expanded measurement uncertainty, and you can measure the output power. And from knowing these two quantities, you can derive the efficiency. And you see, for a typical mechanical harvester, the measurement of the input power is rather difficult. You end up with uncertainties of the order of 1% or something. The output power, which is the electrical one, is the easier thing to measure. But since both quantities go into the efficiency, the measurement of the input power is the dominating factor for the uncertainty of your efficiency. Now, what really is our input power? If you think about a mechanical harvester, I showed you, you can have two different approaches. The one is I showed in the simplified model that you have the electric power, which mechanical power that is in the whole system. But if you look at the curves drawn that you get from those harvesters, if you operate them, you see this is only half the truth. There may be some phase shift between the exciting power and the power that is actually working in the piezoelectric. And so it's maybe a more viable way that you take this phase shift between the two signals into account. I have called it here cosine of phi. And this is only a part of the whole power that you put in. But this is most apparently, this is the mechanical power that is inside the piezoelectric. But again, you will see some more practical methods and details in the piezoelectric workshop, and particularly, I think, in Paul Weber's talk this afternoon. Okay, so let me summarize. Energy harvesting is a powerful tool to harvest energy that is available in the environment as some sort of waste sources that you usually have in machines, either from vibration or heat. There are a number of technologies to provide effective energy harvesting from those sources, as there are piezoelectric, thermoelectric, electrostatic, and magnetostrictive techniques. The efficiency or the effectivity of harvesters has to be determined unequivocally. So you have to describe your measurement system and make sure with traceable measurements of the efficiency of all the input quantities that you have a traceable result for the efficiency of the harvesters. And this assures the comparability of the different harvesters. And these are some metrological challenges in order to find ways to assure this traceability. And to show you that it is not so easy for practical harvesters, even if there are some well-defined engines which are running smoothly, but still there is a lot of vibration, for instance, here for a Ford Focus engine. And you see that the waveform that you get from such a practical harvesters is neither static, neither sinusoidal. So it's some arbitrary signal, and this is something that will be dealt in the next talks. Thank you.
So do we have questions to Bernd?
Hello, my name is Hadash. I'm from Brno University of Technology. I have one question regarding efficiency in energy harvesting from mechanical vibration. There are M. What is it? M.
M is the mass.
Mass and mass of energy harvester or mass of whole system.
Typically, it's the mass of the whole system, of the whole harvester system. In our investigations, sometimes we just had the piezoelectric harvester and some additional tip mass to give some better resonant system.
Yeah, and when I use, for example, harvester which has weight, I don't know, 10 grams, 100 grams, and I use this harvester to structure like this train, helicopter, and a helicopter is, or train has several tons. I have to use this mass of the...
No, it's just the mass that actually excites the harvester.
Yeah, okay. So and I have one question, because this vibrating is seismic mass on the end of the cantilever, yeah?
Yes.
Okay. And if I have a very resonant mechanism with very high Q factor, I can provide very high resonant peak.
Yes.
Okay, and I calculate, I develop several harvesters, and I calculate on the base of this relationship efficiency of my harvester. I have efficiency more than 100%. Because you forgot that resonancy is another mechanical system. You first time provide resonancy, and you have energy from the resonance mechanism.
From the resonance, yes.
Yeah.
Okay.
And if you have very bad resonance mechanism with very bad Q factor, yeah, I have very low. I have very low vibration. I have very low Q factor, a very low
efficiency.
But if I have very high Q factor, very high vibration level, Yeah, I can harvest more energy, but with another efficiency. It means that, okay, what is I'm in energy harvesting? I guess I'm is the best energy harvesting output power.
Yeah.
And you forgot the problem of resonancy, because I can harvest, for example, 1 milliwatt with efficiency, I don't know, 10%. But I have the same harvester. I can harvest, for example, 20 milliwatt, but efficiency also is only 0.5%. What is I'm? The best efficiency or best power?
Well, this is something I wanted to point out. What you really need in practical use is the best output power.
Yeah.
Because this is what industry demands. So they don't want the optimum efficiency, but they want to have the optimum output power. But you still then have to define your measurement conditions in order to make this comparable with other harvesters. Because everybody can say, okay, my harvester gives 100 milliwatts, and I don't know how they excited or have excited this thing to obtain this. And maybe in the practical situation where you use it, you will never get the situation, and you will never get the 100 milliwatts in your practical application. And so this is something, and maybe Paul can comment on this.
Okay, thank you.
Hi, Paul Weaver from MPL. If I could just, we can maybe have a look at this in a little bit more detail in the workshop this afternoon. But I think that for the kind of situations that Roy described, where you've got a large piece of industrial machinery and you're taking out a very small amount of energy from the energy harvester, then the energy harvester loading is not a significant part of the energy budget of the machine, and it's not, efficiency probably doesn't matter that much. But there are situations where the source energy is limited. So for instance, things like human powered devices, then I've seen examples of human-powered energy harvesters that place a significant loading on the guy who's got to power this thing. And so there are some situations, probably outside of the industrial machinery kind of applications, where the efficiency does matter. And I think in terms of the resonant systems as well, then the harvested energy, of course, is part of the damping of the system. So if you have a inherently high Q system, then you'll become more and more limited by the damping provided by the energy extraction. And in those situations, you can, in principle, approach an efficiency of 100%. But I think I would worry if I was getting more than 100%. So, but maybe we can discuss that a little bit more in the workshop this afternoon.
Yes, I think we have at least time for one more question from the audience. No question? Do we have questions here? Please. So, thank you again, Bernd. Yes, and we will come now to Torsten Funck's talk.
Take your time. Yeah, I also would like to welcome everybody. My talk is labeled AC/DC power measurements, and yeah, it's a bit tricky because normally you can have AC power or DC power, but what I use are AC/DC transfer techniques to measure power. And I will explain in a minute how this works. First of all, I would like to give an overview on the contents of my talk. I will talk about methods to measure power. Then I will quite directly come to thermal converters, tell you about the new measurement principles, or probably they are not new, they are only reinvented we have on this. Then I will in detail explain 2 solutions we have developed in this energy harvesting project. I will give you some idea of an intercomparison or some results of an intercomparison and ideas for further development, how we can do this all even better. So as Bernd before pointed out, is that the voltage of energy harvesters may be or is mostly heavily distorted, may not be periodic. For example, on a motor or a pump or so, it will be periodic. But you could also think of an energy harvester mounted in some boots of walking people to charge their mobile phones in the field. Or others may have very long periods. That means if this person, for example, does not move for several times, then there will be no signal. And with the next step, you will have a very sharp signal, very high frequency signal. And this also, another thing is that it will may have sudden changes. And in this project, we use different methods to measure these. One method is simply take an analog to digital converter and sample these things. This has special challenges and will be addressed in the next talk given by Rado Lapuh. I will concentrate, as the name of my talk suggests, on the thermal conversion with the 2 designs of a calculable thermal converter and an isothermal thermal converter. You will explain in a minute how this works. First of all, most of you who think about power measurement think that electrical power is voltage times current, and if you have AC, then also times the cosine of the phase angle in between. This is one approach. You can measure voltage, you can measure current, and you can multiply. This is done, for example, in your energy meter in your home. But I will go another approach, coming more from the definition of the effective value. Maybe you all remember that you somehow have heard that the effective value is defined at that DC value that generates in a resistive load the same heat as the AC current in question does. And this is exactly what we do with the thermal converter, that we simply have a resistor, the resistance of which should be as constant as possible. So we get an electrothermal conversion. In physics, we talk of the Joule effect, which means that the Joule heat, as it is called, is simply the voltage squared over the resistance. And then, as you all know, as you all experience, for example, in a toaster or an iron, this will get hot from the current through it. Then it comes to an thermal model where we have heat conduction, heat convection, and radiation. So we can say that our Joule heat is fed through a thermal conductivity and develops on this conductivity a temperature gradient. This is also experienced that if heat flows through something, then the side where the heat comes in is hotter than the side where the heat goes out. And then we use thermoelectric materials, mainly the Seebeck effect, to convert this temperature difference into an electric DC voltage. And as this in principle works with an AC voltage at the input and an DC voltage at the output, this thing is called AC to DC transfer. or especially the device is called a thermal converter. And thermal converters are quite old, more than 100 years in use. And recently, or not really recently, some 25, 30 years ago, there has been a large step in development, which is a so-called planar thermal converter. This is made up very similar to integrated circuits. So you have a silicon chip, you have a thin membrane on this chip, and etch away everything underneath so that you have a small thermal conductivity here, and you put on a heater, this is this part here, and you put on a lot of thermal converters all connected in series to get a more output voltage and to more equally conduct the heat away, so that you get a more even temperature around this. And all this is about 8 times 13 millimeters and is commercially available from a manufacturer in Germany. So the so-called AC-DC transfer is done in a two-step procedure. Imagine you have an unknown AC and you want to know its effective value. So you apply this unknown AC to the heater and read the output voltage. Then you switch to an adjustable DC and adjust for the same output. And then normally the AC should be the same as a DC with a small error. And the small error, which we normally call delta, is the AC-DC transfer difference of the converter, and has to be calibrated, or for some thermal converters it can also be calculated. I will come to that later. And what I wrote here in the last sentence is very important. To do proper AC-DC transfer, you have problems with drift. Everything is thermal. If you measure the temperature rise above ambient, and if the ambient temperature changes, then of course all your output changes. So you have to do some repetitions to get rid of drift effects. So now I told you some thermal converters are calculable. I will just explain how this is done. And yeah, now it comes to some sampling techniques. We simply record the output of this planar multi-junction thermal converters, this strange abbreviation here, and thus we can directly measure the power in the heater. As I explained before, the output voltage is the number of thermal converters times the Seebeck coefficient of the two materials times the temperature difference. And the temperature rise can be obtained from the energy or the change of energy or power put in, and the thermal conductivity, or thermal capacitance, sorry. And the power, the energy is simply the power integrated over a fixed period of time. So with this, we can, for example, measure the power or energy content of a single pulse. Then I have an enlarged view of the thermal converter. You have here a cross-sectional drawing. You have here the heater, the thermocouples, and I try to explain where the heat goes, which is generated here. Most of it is drained through the thermocouples. No, that's not true. Only a small part is drained through the thermocouples. Most of it is drained through the air, and a little bit is drained through radiation. So this gives us a model of the thermal converter. You have here the thermal capacity. You have here the integral of the power, and the power is the electrical power which is transferred by the heater resistance to thermal energy or power. And we have here some feedback which gives the heat flow I just explained through the thermocouples, through radiation and through the air. And then it comes out with our temperature rise, and the thermocouples convert this to the output voltage. All this done has precisely characterized so that we get all these functions and coefficients here. And we made up a mathematical model in MATLAB Simulink. And with that, we can then work our thermal converter, so-called backward. First of all, I would like to show you how we characterize the thermal converter. Since it measures the temperature rise above the ambient, we also measured the ambient or the cold side of the thermocouples by means of a platinum-100 thermometer, which is driven by a constant current, and the voltage is measured. These devices here are well-known voltmeters, and we have an also well-known voltage source, which gives us the power through the heater. This is done, set up as a current source, and so we apply a known current through the heater and we measure the voltage difference, so we also get the heater resistance, and from voltage and resistance or current and resistance we can calculate the power. So then what is interesting in this device is also the frequency response. Normally some AC-DC transfer is done in the frequency range from about some hertz, or at least 10 hertz, up to about 1 megahertz. There are devices that go up into the gigahertz range, but this are not addressed today, because also in our project we said, okay, we limit to 100 kilohertz. And what we measured here, I told you in the very beginning that there is an AC-DC transfer difference, which mainly comes from the heater resistance, which is not the same for AC and for DC, because it has some inductances, it has capacitances, so the real part of the heater impedance is not equal to the DC resistance. This is the main source of this frequency behavior. But if you look here at the scale, this is microvolts per volt, so other people call it parts per million. And it is well below 100 parts per million, which also was the goal in our project. We tried to measure everything in the order of 10 to minus 4, which then is 100 microvolts per volt in this case. And the other thing is, if you can calibrate something, okay, here are no uncertainty bars, you can also correct for it, if that should be necessary. So this is not really a drawback in performance. So we made some test measurements. By the way, this setup can be viewed outside in the coffee break. No, not this one, the next one. But this is works very similar. So what we did is we generated a rectangular pulse from a well-known voltage source and a switch. And we measured, of course, this pulse with a digitizer, and we applied it to our thermal converter, and we digitized also its temperature and its output voltage. Here in the insert you can see that we first start the measurement, then we switch our pulse, and then we stop our measurement. And you can see the results here. This may be not quite clear what it is. The thing is that we have here the output voltage, then it goes down, that we calculate the some electric power, and from that we calculate the input voltage, and this is the measured input voltage, and from this we can calculate the power of the pulse that we applied. And since we have measured this independently, we can also give you some uncertainties. So we say that we can measure the power with about 2 milliwatts per watts, and also the energy. And the voltage, of course, is only 1/2 because it's voltage squared over resistance is the power. This is slightly more than our goal. Not slightly, it's 20 times more than our goal, but it could be easily improved by operating the thermal converter in vacuum, which was not done due to timing issues. We simply had not the time to develop this. So the next thing is that we try to operate a thermal converter isothermally. I will just explain how that works. The thing is that a thermal converter to operate properly needs a constant output voltage in order to, since it's a DC voltage, in order to measure this. We had just overcome this by sampling the output voltage, but we can also do another approach. Then that means that the input signal, if the frequency becomes too low, then of course the output voltage will follow this low. This is just what we used in the approach before. And if the repetition rate is too low, then we also will have pulses on the output voltage. And the remedy is quite simple: keep the output voltage constant. That means we have to keep the over temperature constant. And this is done by applying a regulating power. If we have here in red the input power, we need a second power source, which makes simply this blue area here to maintain a constant output power. And this regulating power is inserted by a thermal converter which is fed by two voltages. One is the input voltage to be measured, and one is a regulating voltage from a controller. You can see this in this schematic diagram. We have a thermal converter with two heaters. I will just show you in a minute how this looks like. Then we put we amplify the output voltage and compare it to a voltage reference and put it to a controlling circuit, which the output of which is fed back to the thermal converter, to the second heater. And then we measure this output voltage instead of the input voltage, and have here now the advantage that we have the full bandwidth up to megahertz of this device, with sampling here only some 100 hertz or kilohertz. So maybe it's a bit difficult to view here that we have applied here a second heater above the first one. Maybe better in this view. So we have this first heater made of nickel chromium. Then we have a layer of gold, which normally makes our contacts. And in this layer, we simply changed this one mask and made a second heater on the first heater, which is far away from optimum, but it was easy to do in the limited time of the project. Then we mounted this in a heavy enclosure to get rid of environmental changes of the temperature. And now we have a thermal converter that consists of two heaters and one string of thermocouples. And since we want to substitute the power in one heater with the power in the other heater, we exactly have to know the properties of the heater, or especially how the heater works on the thermocouples, how much power generates how much output voltage. So we put all this in a thermoregulated enclosure, fed in again a current, measured the voltage, and the output voltage of the thermocouple then did the same on the other side and characterized the two heaters. So now we have a device that can substitute regulating power with a measured power. And you can see here, if we have an input step of 1 volt, how the output voltage first has some excursion, but then the controller comes in and it returns within a few seconds to within 10 to minus 4 of its value. Again, the frequency response looks a little bit better in this case. I don't know why, but it has here we have uncertainty bars. You can see that everything also is again well within some 50 parts per million or plus minus 50 parts per million. What is interesting here is an offset of about 20 microvolts per volt. This is simply due to the imperfect characterization of the two resistors I just told you about. This is not really an error because it can be calibrated and can be taken into account. Here we have the AC-DC transfer difference, which again goes down to about some 80 parts per million at 100 kilohertz. And here we measured also up to 1 megahertz, where we then have about 100 microvolts per volts. And so this could be used as a standard AC-DC transfer device also. I told you that you have to repeat AC-DC transfer a lot of times in order to get rid of drift. And here you again have the advantage that due to the regulating loop or the control loop, everything is significantly quicker. Normally for a thermal converter, you have to wait about 50 seconds, 1 minute. Here you have to wait 5 to 6 seconds. So we get an improvement in speed of about a factor of 10. Which could lead, if we would do this consequently, to greatly reduced measurement times. Maybe we will do that, we will have to think it over. Oh, here also we measured a rectangular shaped pulse. We also have our well-known voltage source, our switch, our digitizer, and again, the measurement time is of course longer than the pulse, and from with one channel, we measure what we put in, and with the other channel, we measure the output. And this is recorded here. We have here our pulse we measure, and here we have the output voltage of the regulator. You see here some heavy, that does not really work well, but we have a large pulse of 1 volt here, which is almost full scale. And you can see here that here the protection of the thermal converter comes in, which we built fearing not to damage the thermal converter. We limited the regulating voltage. And even with this limit here, we get quite a good measurement deviation of about 5.5 millijoule per joule, which is again about 5 times what we would like to have. But this is the full scale measurement. So summarizing, I could say isothermal or calculable thermal converters have, contrary to direct sampling, a very wide frequency range up to 1 megahertz. They have transfer differences as low as thermal standards, but much less waiting times. The main advantage is that we can now measure arbitrary waveforms and even single pulses. We can choose whether we would like to measure the effective value, that means an equivalent DC, or if we would like to measure the energy content in a pulse. You may consider situations where an effective value is not really useful, that it's better to say, okay, in this 10 seconds we had this amount of energy. Intrinsic accuracy is limited by the calibration of heater resistances, but you can always use a sine wave to calibrate it, or you can even use DC to calibrate it. and the combined uncertainty is about 0.4, 0.5 millijoules per joule. So, thank you for your interest and questions.
Yes, we have about 15 minutes for questions and remarks. So, please.
Rado has a question, I think.
So what is the expected improvement in uncertainty when you will go to the vacuum realization of this device?
About
and also other things like waiting time and things like that. What would change actually? If
what is changed actually? Yeah, I can have to go back some slides. Sorry for that. This can be quite well explained here. You see here that here is a very small gap between the thermal mass below the heater and the base where the thermal converter chip is mounted. And this gap is in the below, I think, 0.5 millimeter. So if due to thermal expansion this will bend through, then this will change a lot. And it's difficult to calculate the heat flowing out here if everything gets hot. And if we would have vacuum, then the distance here could change without changing too much the thermal conductivity. So we calculated to get an improvement of a factor of about 15 to 20 from going into vacuum. So with this thing operated in vacuum, we would be well below 10 to minus 4 uncertainty. Some 0.5, 0.8 times 10 to minus 4.
My second question would be, what is the dynamic of this device if you go with the amplitude of the signal up or down, actually down, yeah? If you measure the full scale signal, then you get the uncertainties and the outputs as explained here. But what is the dynamic if, for example, if the signal is 10 times lower, what that means for such a device?
The dynamics is, yeah, you have to distinguish between the bandwidth of the device and how it follows the power of the input signal.
Yeah, I meant for the power.
Okay.
The power goes down, yeah.
Yeah, this is, I think, within seconds. But normally we have, or we are interested in the energy content over a given time interval. And this is, of course, reproduced exactly because of the integrating part in the control loop. Even though in the transient times, we will have some differences of the, I will try to show. We have here this curve. That means the step goes somewhere here, and then it remains here. So we have for about 2 seconds some excursions of the operating point from nominal. But if you extend this over 10, 20 seconds or so, then everything's okay again. So here after 2 or 3 seconds, the device is again at its operating point. For example, if you would apply a ramp on the output, then you, of course, would have a constant difference. But if the ramp somewhere stops because it cannot go to infinity, then everything would come to the operating point back again. So during a ramping input signal, we could not measure, but if the ramp stops somehow or at some time, then if this is included in the measurement time, we have no problems.
Well, if I would ask a different way, you have a 1 volt range device.
Yeah.
If you measure 0.1 volt, does that mean that you already need to use amplifier for actually accurately measuring the signal? Or if you go to the 10 millivolts, you have to use the amplifier, or is the device still okay to
I would not use it to less than 5% of its nominal output. Probably only down to 10%. Okay, that's so another thing one has to admit here, that thermal devices, since they measure the power directly, of course, are going down only to, let's say, have a dynamic range of about only 1 to 10 or 1 to 15 or at most in power, because the output voltage is related to the power. That means you have a dynamic range of 1 to 6, 1 to 10 in voltage or current. That's the main limitation of all these devices, which measure in principle the square of the voltage or the square of the power. You have the same with electrostatic MEMS devices, with thermal devices, because of their quadratic transfer structure. So this limits the dynamic range, of course.
Yeah. Thank you.
So I have one stupid question. Perhaps I missed something in your talk. What's the reason for the increased uncertainty at higher frequencies? And is there a possibility to shift your device to measure also for higher frequencies accurate?
The main cause for the uncertainty or for the measurement error at high frequencies are that the heater resistance is not a pure resistance, of course. I showed you that this looks somehow like, what is it? Wrong way, sorry. We have here this so-called bifilar heater, so that means this is this shape here, and this can be treated as a transmission line, and at higher frequencies you have more losses due to capacitances and inductances. Also, you have the inductance of the bond wires, which connects the device to the outside. And you also have resonances with the inductance of the bond wire and the capacitance, for example, of the bonding pads and so on. And this limits the usable frequency range to about 1 megahertz. Another thing is that the substrate is silicon, and it's not pure silicon, it's doped silicon, so it has a finite conductivity. It's not an ideal isolator. And so you get losses also at higher frequencies due to capacitively driven currents in the substrate. The remedy is to put all this on another substrate. We have thermal converters on quartz. This can be used up to at least 300 megahertz. We've not just tested this fully, but it works. And so this would be one idea. The other thing is that in this setup, we always have quite long transmission lines, wires, from the beginning of the heater to our reference plane. You know, at high frequencies, you don't operate with connectors. You define a reference plane where a special power is measured. And this is not optimized for frequencies above a megahertz. Then we would use other connection techniques. So using quartz, the limit would be, I would say, 100 megahertz. But I have to stress that this is not the goal of the project. This project was clearly limited to 100 kilohertz because energy harvesters normally do not produce high frequencies, except if they harvest, for example, power transmitters or something like that. But even then, this could be avoided, I think.
Yes, there is time for one more question. Okay, as there are also no questions from the webcast, we can now come to the next speaker, which is Rado from SIQ.
Yeah. Great. I'm okay.
Thank you. Hello, everybody. I'm Rado Lapuh. I will present the work similar to what was presented by my colleague, Torsten Funck. But this is the part when we used sampling for measuring the voltage, current, power, and energy. This work was done jointly by SIQ, the INRIM, and PTB, and I will present this in the next 10-15 minutes. I will try to show you the challenge we had, and from that I would go to the problem of generating the signals which were useful for our measurements. For the sampling, to the sampling instrumentation used to sample these signals, to the estimation of these samples and how to calculate the power, the voltage, RMS, and the energy out of these sampled signals. And that was the main part, actually, of our work. I will tell you why. And then I will come to the uncertainty of these measurements, and I will present some conclusions on that. So the challenge was, as you already know now, to measure accurately the arbitrary waveforms, signals, and their power in the frequency range up to 100 kilohertz with uncertainty of around 10 to minus 4. This challenge was, we wanted to generate such signals. We wanted to measure them by thermal principle, by sampling principle, and to compare these measurements so that we know that we actually do the thing right. Yeah, and we can prove that our traceable measurements are okay. So we first defined some signals which are not sine waves, as are usually used in metrology for very, very precise measurements. We then sampled that signals with known uncertainty. Use these algorithms we either developed or took from the literature and estimate uncertainty on them. So that would be a real harvester example. Yeah, this is the signal from energy harvester for tire pressure monitoring system in the cars, and you can see that this signal is far away from being a nice sine wave or whatever. It is simply the response to the pulses in the tire. But we can see some repetition, some periodicity in the signal. And this is what we are counting on. This is a piezo example, and we can see that the frequencies in which this particular kind of harvester is operating is around 1200 hertz. Yeah, 1 kilohertz, 100.2 kilohertz. So, in order to actually do a really precise measurements on non-sinusoidal signals, we used to define some signals which would help us do that. And we decided to make our comparison measurements on those three signals, on cosine shape bursts, on raised cosine, and dump oscillator waveforms. We had a reason for choosing these signals. First, we wanted to have repetitive signals. Without repetitive signals, we could not do actual stable measurements. That was one thing, because we cannot make measurements in the exactly same time with one sampler, another sampler, and thermal system. So the first signal has one frequency and two sidebands, which are common to some excitation models, likely because there is one actually a signal in which is modulated. Yeah? These signals are not harmonically related, and this is typically a problem for metrology measurements. Yeah? How to evaluate RMS values. The raised cosine has a quite full low frequency band, yeah? And then sharp roll off, so that we have no no aliasing effects and things like that. However, we have a lot of energy in these low frequencies. And in dump oscillator is actually a quite typical oscillator of system of second order, which is kicked on every time, so that energy is brought in and the harvester brings that energy back. And we see from the frequency spectrum that we have a lot of energy and a lot of harmonics all over the place. So that was the challenge for our signals we were using. And for the signal generation we went we took two approaches. We designed a generator prototype, very accurate and stable generator, and also we were using the commercial alternative arbitrary waveform synthesizer. For some reasons I will explain later, the commercial alternative was actually used for our measurements in the comparison, and for some good reason. For what we did for our measurement, this is a schematic show. We actually used our generator, and we loaded the thermal converter, which was actually used for the measurements. Yeah? And we used the 10 ohm resistor to actually also measure the current through this system. So we sampled the voltage with one sampler, and we measured the current, which was actually a voltage over this resistor, with another sampler. So this is a principal scheme. We used two samplers, and so the scheme was a little bit more complicated. But this was the principle. And of course, the samples need to be synchronized to measure the power. The sampling instrumentation used. So the INRIM used the Agilent 2542A analog module, ADC converter, and we used the well-known 3458 Agilent multimeter, which is extremely accurate, and we know it very well. And requirements on the instrumentation were we should have flat response, especially in the signal band where we have strong components. We have to be flat. We have to have, let's say, adequate response in the residual harmonics band, so where the power is not so does not affect our values. We should still have a response, but it's not necessary to be as accurate as in low frequency band. We should have fast enough sampling rate, of course, and the huge continuous sampling capability, which is not a problem for the USB module, but it was a problem for this voltmeter, which we solved during the project, so we could read samples in real time with whole resolution. Now, I'm sorry to go to the formulas, but this is important for a thing. The definition which we are measuring is the RMS value, yeah, of the signal. And it is defined in that way. It's the same for voltage and for current. We can measure the current, as I showed before, by measuring voltage across the resistor from which the current is flowing. So if we know how to measure the RMS value of the voltage, we also can measure the RMS value of the current. If we have a very good resistor, of course. The power is defined a bit different than the RMS value of the voltage, but we can change this formula to that one on that right side by using the square root over the voltage multiplied by current. And actually, we got the formula which is quite similar to this one. So actually, the RMS of this square root of U times A, voltage times current, is actually the same formula, this one. And if we take this squared, we get the power. What means if we can measure or estimate RMS value, we can estimate power. Yeah, it's the same principle. So we don't need to go into details how to measure power, because we will solve it by estimating the RMS value very well. And energy is just the power times time, and time is a number of samples times the sampling time, which is trivial again. Yeah? So in my further talk, I will just talk about the RMS value. That's why I went to the formulas. One problem with these formulas, or with the use in the samples we have, these equations are valid only for integer number of signal cycles. Yeah? But harvester cannot be synchronized, and we have some arbitrary things in them. The frequency can change. Whatever we've been hearing here, a lot of times the signals are not stable at all. What means we cannot catch the actual condition of having integer number of samples in measurements. So what to do? So we cannot use these formulas directly. We have three solutions actually. One is the long time averaging, actually what would be the analog principle, that we measure as long so long that the result becomes stable. Yeah? Then we have good result, but this is really overkill work. Yeah? We have a possibility to quasi-synchronous sampling, or we can use windowing in time domain, which I'll explain now. The quasi-synchronous sampling goes in that way that we estimate the frequency of the signal, the base frequency, lowest frequency of the signal, and then we cut the last non-integer part of our signal, and we calculate the RMS using the original definition formula. The other approach is to use a windowing in time domain, so that we apply a window over the sampled record, and we calculate the RMS value of such windowed record, and then we multiply by square root of the normalized power gain of such a window, and we correct for this shape back to this signal. Yeah? If we look what happens with one or another approach, for a sine wave with a little bit harmonics added, we find out if we use a simple classic use of the formula without any synchronism, we get quite high errors. Yeah? Of course, these errors go down when we are around integer number of signal periods. If you use this quasi-synchronous sampling with some interpolation, so that we really find a good the integer number of samples, integer number of cycles, we reduce these errors by factor of 10 to 100. Yeah? But this is still not enough if we use only a few signal periods. Yeah? If you use windowing, we can see that this error goes down very rapidly. Yeah? So in a few signal periods, we actually go down to the noise level of such a signal. Yeah? What means that the windowing principle is quite promising for this use. Only when we have really a small number of cycles, like 2 or 3, yeah, this quasi-synchronous sampling and the interpolation might work better than windowing, yeah, when the windows are really not as good, as you can see here. So that's for the sine wave signal. If we simulate our signals we use for the comparison, for the cosine shape burst or for damped oscillator, we see that the windowing approach is a little bit worse in a manner that we need a little bit more signal periods for our measurements. But still, when we go over the 5 or even over the 10 signal periods, yeah, we see that we come to the noise level, and actually the windowing is working perfectly, really perfectly. The errors are around 1 10 to minus 6 or so. Yeah? For the damp oscillator, it's about the same. It's a little bit different shape, but you can see that, that the errors go down very rapidly and very quickly. So we don't need to wait a lot of time with our samples to catch 100 or 1000 periods, but we can calculate our power much quicker. So what we done further on, we checked the very well-known signal. This was the AC signal from Fluke 5720, a reference calibrator, yeah? And we use this windowing approach and another sine fit approach, which we know very well. And we used 10 periods signal, so 10 periods window on the signal, and we moved this window across the signal to see what is the response. And we saw that we have something like 30-40 ppm deviations in the signal. This is a known thing in this calibrator because it's not so stable in a short time period. Yeah, it has some internal loop to correct the output voltage. When we extended this to the 100 periods and the frequency of the signal was to 200 hertz, yeah, when we used 200 periods, so this is the 0.1 second time, we already came to something like 2 ppm stability, and this proved us that this actually windowing system is really working perfectly. Yeah, we actually got the results which we expected. Then we went to our sine wave generator, arbitrary waveform source, and generate sine wave, and we saw that we have something different than before. Yeah, we have some more deviations in our measurements, and this is what we thought that it's of use for us, because we see that there are some drift of the output of such a generator, and we know that harvesters are nothing like very stable devices. Yeah, they have drifts and so on. So this could be of use to actually simulate, additionally have some drift and see if this is really influencing very much our measurements. Yeah. So we saw that if you use 100 periods window, the stability is within 50 ppm or so. But if we extend this period window to a longer time, we see that all results are coming together, yeah, to actually very, very, very accurate signal. When we use this cosine shape burst, we see the results are all also coming together, not so exactly at the end. There is some difference of something like 15 ppm or so, but this is due to, as is shown here, due to not very well estimated frequency of the signal, and so the interpolated algorithm didn't work very well in that case. So that's the reason why we got these errors here. Otherwise, other free algorithms by using other different windows came together very well. The RMS, the raised cosine wave showed the same results with only 25 periods windows. We got very good results already. And for example, the dump oscillator with 50 periods window also results were within 50 ppm. Yeah? And here are the actual spectrums from our sampled signals. So my comment on the algorithms, which was the main outcome of our work, was that classic algorithm, actually, to just using a formula would not work except for averaging extremely long sample record. Yeah? The quasi-synchronous approach would be good if you have only a few periods of a signal. That could work. Otherwise, you will not get such a good results. Windowing in time domain is really an option of choice, especially when you take more samples and you use signals with more than 3-4 cycles in the record. For the uncertainty, these are uncertainties which we came up with our measurements. For the sampler flatness and DC accuracy, we could reach better than 10 ppm specification easily. For the algorithm, we already showed that we get less than 2 ppm errors using windowing approach. Noise and signal stability were around 20 ppm, taking the windows which we used. If we would take longer windows, that might go lower too. So the combined uncertainty came up around to 23 ppm for such a system at 1 volt level. Of course, we have to take care that the sampling time selection is always according to the Nyquist theorem, so that we don't have any frequencies or any significant signals above the Nyquist frequency. And the number of sample selection is such that we sample more than 10 periods, at least more than 10 periods. So that's the requirement. For the conclusions, for the sampling hardware, which is necessary to measure the voltage, power, current and energy, actually there are no real special requirements except huge memory, which we use to sample all these samples. However, if you know what window you will take, or what is your lowest frequency in the signal, and you decide that your window is fixed, and you're using a DSP or such a thing, actually the calculations can be performed on the fly, and you actually don't need any memory. That's a real advantage of this system and of this windowing approach. You don't need any post analyzing of any data before, because you can just collect them and sum all of them, multiply them on the fly with the windowing function, and at the end you get the power out or the RMS out. So that's a good thing. The sampling parameters, as I already said, twice the highest expected frequency, and the number of samples to capture more than 10 single cycles. The algorithms, I will just point out one: windowing in time domain. This is the way to go. And well, at the end, windowing in time domain, I guess, and I'm sure it's also the way to measure the. Now we show that this is the way to measure the multispectrum signals very accurately.